In this video, we're going to talk about parametric equations for lines, circles, and line segments. These three are the most important ones that we are going to use later on for line integrals. So let's start by parametric equation of a line. So if you remember, for writing equation of a line, we said that we have x, y, and z in a space. So x would be x naught plus the parameter t a, y naught plus tb, and z naught plus tc. And basically x naught, y naught, and z naught, these are the point on the line, so it's a point on the line, and A, B, C is basically the components for a vector in the direction of the line, direction vector. So it's a direction vector. And basically this parametric equation of the line would be the one that we are going to use for parametrization of a line. As an example, if we have r of t as 3 plus 2t, negative 5 plus t, and 10 minus 7t, okay, where t is in the r, then we're going to say that this is the x component, this is y component, and then this is the third component or z component of the parametric equation of the line. So we parameterize our line like this, basically writing parametric equation of the line, and this would be our parameterization for the line. Then let's talk about parametric equation of the circle. Parametric equation of a circle. So assume that we have a circle x squared plus y squared equals to 1. Then for parameterizing that circle, okay, it's a circle in R2. Let me graph it. So I have x-axis, y-axis, and then, oops, I have this circle. Of radius 1. And to parameterize that, I'm going to say that the x component is cosine t, and the y component would be sine t, where t is between 0 and 2 pi. And it makes sense. Why? It's just because let's start from t equals to 0. At t equals to 0, I get cosine of 0, which is 1, and then sine of 0, which is 0. So at t equals to 0, I'm here. Okay? Then if you plug in different t's, for example, at t equals to pi, I get cosine of pi, which is negative 1, sine of pi, which is 0. So negative 1 and 0. So I move along the circle at t equals to pi, I'm here. Then just plugging different values for t, and then for example at here, at t equals to 2 pi, I get cosine of 2 pi, which is 1, and then sine of 2 pi, which is 0. I go back into here. So I go around the full circle of radius 1 when t is between 0 and 2 pi, and I get this circle. That's why we use this along with the domain or the range for the parameter t as the parameterization. Now, can you say what should we do if we have a circle of radius a, for example? That's correct. We should say r of t would be a cosine t and a sine t, and it's important to write the range for t. Sine t, where t is between 0 and 2 pi. Great, that's important one. Let me ask you a question. So, question, if I say r of t is cosine of 2t, sine of 2t, where t is between 0 and 2 pi, okay? What is this? What is this curve? As you see, I still can say this is the x component, this is the y component, and I know that cosine square of any angle plus sine square of whatever of 2t, for example, here would be equal to 1. Cosine square plus sine square is equal to 1, so I still get the circle. Let me graph the circle. I still get this circle of radius 1. This is x-axis, this is y-axis. But let's see. Let's look at the range in here. At t equals to 0, I get cosine of 0, sine of 0. Cosine of 0 is 1, so at t equals to 0, I'm here. Then I'm gonna move along the circle, but let's plug in t equals to pi over 2, for example. At t equals to pi over 2, I get cosine of 2 times pi over 2, so I get cosine of pi, which is -1, and sine of pi, when I plug in pi over 2 into here, which is 0. So as t equals to pi over 2, I'm here. Then, if I say at t equals to pi, I get cosine of 2 pi, which is 1, sine of 2 pi, which is 0. So at t equals to pi, I'm here, and then I just keep plugging different values for t, and at t equals to 3 pi over 2, just plugging in here, I get cosine of 2 times 3 pi, actually, times 3 pi over 2, and then sine of 2 times 3 pi over 2. So I get cosine of 3 pi, which is -1, and sine of 3 pi, which is 0. You see, at t equals to pi over 2, I get to this point, and at t equals to 2 pi, I get to this point. Okay, so this circle, it moves, this curve moves twice around the unit circle. So as you see here, the range is very important along with the function. Now let me ask you one more question as a kind of a note. Let me give you a note. What happens if we have a circle of radius a, but yet at a different center, not at the origin? For example, at the center here, h and k, and the radius, for example, is a. X-axis, y-axis. So to parameterize that, I can say that x would be h plus a cosine t, and y would be k plus a sine t. Therefore, the parameterization r of t, if I want to parameterize a circle at the center h and k, it would be h plus a cosine t and k plus a sine t, where t is between 0 and 2 pi. You can say when t equals to 0, I get cosine of pi, which is h plus a, so I'm gonna be here at t equals to 0, and it moves. Now let's look at the last one, which is parametric equation of a line segment. And what is that? What is a long segment? Just assume that we just have part of the line from P with the coordinates 0, 1, 2 to the Q with the coordinates 2, -1, and 4. Okay, now to write the line segment in here, let's look at equation of a line. If we have a line and R0 is here, R0 is just one point on the line, then I'm gonna look at the origin and I'm gonna make a vector in here. So the vector 0, R0, then I have any point on the line. For example, let's assume that this is a point R on the line, and I have this vector R0R as the direction vector of my line. So OR0 plus R0R, the vector R0R, would be this vector in here, OR, right? So OR0 is just the coordinates of R0 minus 0, 0, 0. So I can say that the vector R0 plus, oops, I forget to put the parameter t. Why do I put the parameter t in here? Because if I have just one copy of the direction vector, I'm gonna be here. So if I, instead of t, I have 1. Then if I have another copy of the direction vector, I'm gonna be on this part of the line. Okay, so this part, to write this part of the line, I get R0 plus 2 times R0R, and I get to this point. If I want to write just up to here, if I want to get this point, it would be OR0 plus half of the R0R. So for any number that I put instead of the parameter t and change the direction, change the length of the direction vector, I get a different point of the line. That's why it's important to have the parameter t in here. And then it would be R minus R0, and it would be equal to R, right? So now look at this line segment in here. I'm gonna say that I'm gonna start at this point, which is the point R0. Then I get 0, 1, 2, and then plus the parameter t. Then I have R minus R0, which would be this minus that, Q, P, okay? So it would be 2 minus 0, -1 minus 1, and then 4 minus 2, and it would be equal to any point on the line. So I get what? I get 0 plus 2t, and then I get 1 for that, plus t times -2, so it would be -2t, and then I get 2 plus 2 times the third coordinate, 2t. This would be R of t, where t is between 0 and 1. Why? It's just plug in 0 for t. If I plug in 0, I get 0, 1, 2, which is the beginning point. So at t equals 0, I'm here. If I plug in 1, I get 0 plus 2, which is 2, and then I get 1 minus 2, which is -1, and then I get 2 plus 2, which would be 4. So at t equals to 1, I'm here. So to get the whole line segment, all I need to know is just put parameter t from 0 to 1. That's why this is the parametrization. Now let me summarize what I did. I'm gonna say that formula for line segment, this P and Q is this: R of t is p0, the first point actually. Let me just say p, the first point, plus t, and then I'm gonna say q minus p, and where t is between 0 and 1, this is the parametric equation of a line segment. T between 0 and 1 is very important. As you see, if t equals to 0 in here, this part would be 0, so I just get p, the first point. If t is equal to 1, if I put 1, I get p plus q minus p, so the p would be cancelled with that p, I left with a q, which would be here. So these three, line segment, line, and circle, are very important later on. That's why we went over them.